Hi, good morning. Today we will discuss about some problem on the viscosity. The title is a property of fluids. The viscosity also for the first problem, viscosity problem. The problem number one, the space between the two square flat parallel plates is filled with oil. Each side of the plate is 60 centimeter. The thickness of the oil film is 12.5 mm. The upper plate, which at 4.5 meter per second, requires a force of 98.1 Newton to maintain the speed. Determine the dynamic viscosity of the oil in the coils and the kinematic viscosity of the oil in strokes if the specific gravity of the oil is 0.95. So in this problem, some data. So what are the data given here? The first we have to write it. Before write the solution given data, first write it. So the square flat plate, so 60 centimeter area we can calculate 60 multiply 60, right? So otherwise we convert to meter. So 0.6 meters, 0.6 meters, 0.36 meters square. And dynamic thickness of the oil film dy is a 12.5 mm, the thickness of the oil film, right? So 12.5 go minus 3 meter, and the upper plate. So this velocity is 2.5 meter per second. So here you take a bottom plate will be constant you take, right? So here this 0 degrees 0 meter per second. So you take a changing velocity between the plate du equal to 2.5 meter per second. So the force vector on the upper plate, how much the force you are giving to track here, 98.1 Newton. So shear stress calculate force by unit area. So force 98.1 and the area equal 0.36. So you get a value, shear stress value also. So how much is shear stress? Yeah. So shear stress approximately how much is coming here? This 38.1 So you get the value Newton per meter square. Then you submitted dynamic viscosity. So as per the Newton law of viscosity, tau equal to nu dou u by dou y. Nu equal to you get the value, right? Tau value. So you get the value with this. And here equal to nu dou u by dou y. So changing velocity 2.5. Ty equal to 2.5 turbo minus 2. So new value, how much that is minus 6.5 twice. So this value 1.3 Newton second per meter. Okay, convert to Bys. So 1 Newton per second meter is equal to 10 bys. So you get the value 13.63 bys. Okay. So next you take dynamic viscosity. Dynamic viscosity, you know, here is dynamic viscosity by density of liquid. Density of liquid basic gravity is given in the problem, right? 0.95. So you get the value multiply of 1000, you get the density 950 kg per meter cube. Then you put your value, you get the value for this dynamic viscosity. So that is value centimeters per second, you know, you convert to. So 1 centimeters per second is equal to 1 stroke. So how to convert meters per second value is given, right? So you convert to centimeters per second. So 10 power 4 multiply, right? So here there's you get the value 14.35 strokes. Okay. So this is the first problem. Over. Second problem, that is here dynamic viscosity of the oil used lubricating between the shaft and the sleeve is 6 pies. Okay. So here what viscosity is given? Dynamic viscosity. Second, the diameter from the shaft is 0.4 meters and rotates at 190 rpm. Calculate the power loss in the bearing for the sleeve length of 90 mm. Thickness of the oil film is 1.3 mm. So now you put a value. So here one by one you are writing the given data. Next you find out here this tangential velocity of the shaft. So you know here this u equal to by d and by 60. So get diameter's value, you know, given 0.4, n value 190, divided by 60, you get a value. Tangential velocity of the shaft, you know, here there's 3.98 meter by seconds. So next here this velocity, next Newton law of viscosity, tau equal to nu dou u by dou y. So new value here, uh, unknown value, right? So already given, what are the data is given? Velocity change is given 3.98 meter per second. Thickness change is also given. Next you put it tau equal to, yeah, there is a poise is 10 poise is given here in dynamic viscosity. Then you put in the value tau equal to 1.92 Newton per meter square. Next, what you find out force. Force equal to shear stress into area. So stress equal to 1.92 into ideal. So here is 0.4 into L length, 90 into 10 to minus 3. So you can have value 180.0.5 Newton. So that's the torque. Torque equal to force into perpendicular distance. Otherwise, radius you take. So this is force into d by 2, right? So that value you get the value torque. That's the power loss also of is 2 by 60. So that's value matter. So otherwise, we find out here is a torque into velocity also put it the same value you are getting that is okay. So next there is the third problem. So these are two larger grain surface are 2.4 centimeters apart. The space between the surfaces is filled with the glycerin. What forces required to track very thin plates of the surface area 0.5 square meter between the two largest plane surface at a speed of 0.6 meter per second. The thin plate here is in the middle of the two plane surfaces and the thin plate is at a distance of 0.8 centimeters from the plane surface. Take the dynamic viscosity of the glycerin is 8.1 into 10 to minus 1 Newton seconds per meter square. So now, this concept are two cases you take. First case is what you take here is the thin plate will be tracked between the glycerin, but it is a middle portion. Middle portion means the total length. This is 2.4 centimeter, right? So what happening here? This middle means 1.2, 1.3 you take. Okay, in thin plate. So here now you take a force. So it will be F1 also, F2 also calculated. F1 means um, tau equal to mu dou u by dou y. So now tau 1 also calculate. Tau 1 mu also already given, right? 8.1 glycerin dynamic viscosity 10 by minus 1. So T value 0.6 velocity. So this is a thickness top. First you take the top and this is 1.2. Okay, 1.2 centimeter. Take the 0.0. So now you take this 40.5 Newton per meter square. Same thing F2 also calculate. Same procedure you follow. Quantum also you take tau 1 and tau 2 also. Tau 2 also you calculate. So this is tau 1 value, tau 2 value also same. So 40.5, 40.5. Next here this stress also. Okay, tau 1 40.5, tau 2 40.5. So M2 equal to tau 2 by A. So A value 0.5, right? Right? So both values also top to the bottom also force also will be equal 0.20.2 by 20.2 by total 40.5. This is the first case. Second case, when the thin plate at a distance of 0.8 centimeters from one of the plane surface, previous case, so this position first is a 1.2, right? Second is a downwards, this is a bottom is 0.8, remaining how much 1.6. So first you take this a top, see it is how much here this. So tau 1 you calculate this and tau 1 here, tau 2 also calculate this. Okay, so tau 1 gives this and tau 2 also. So next force also calculated this, right? So the force tau 2 A equal to this nu dou u by dou y to A like this. Now so this one also dy 0.8 to bottom. So top it is 1.6, right? Otherwise you take this value here. So get 13.36 after 14 by 1 total and how much you get this 40.54. So what's the difference between the first case? second case. First case, if your middle is moving, how much total force is effective? 40.5. In second case, 43.5. So, flow downward direction is moving, heavy force also you are giving to the plate. So that's what will happening here. This total force also required will be very high. So what happening here? This is the few intensity pressure also will be acting. So in pictures you have to study this here. Pascal the hydrostatic law, the concept will be clear. But in this case, here this what is the differentiation between first case to second case? First case middle is moving mean 40.5. Second case this here 45.4. 45.4. Newton mean. So heavy force will be needed for the dragging the plate, right? So what happening here is in uh, this lecture is called Pascal and hydrostatic law. So I think here this is the fourth problem. The plate will be positioned blade vertical direction. See in this case what will happen? So here this minimum portion is 1. So normally plane with thickness is a 0.4. So what happening here? This is a 2.4. Here we go. So gravity force also is given. So now this case SCL force will be acting side to side and the lifting force also positive. So now you take here this weight of the liquid force you call the weight of the liquid means what? Suppose the plate will be inside the liquid, means what will happen that volume of liquid will be replaced, right? So that value of the calculate is there W equal to rho is this. Otherwise here this you know here this density also you know here this and rho value rho into g otherwise specific weight specific density of the otherwise m into g also here this you will take here this. So now you can take here this yeah mass value. So weight density equal to W equal to m into sorry rho into G. Rho value you know here this 900. G value 9.81 is the value. And the volume of the plate also calculated. This volume you know 1.2, 1.2, 1.2. So thickness of the plate you know. Velocity of the plate and weight of the plate here this. So now you take this mid portion how much 1. Okay, 1 centimeter 0. Okay, as here from 1 you calculate this. Okay, so new dou u by dou y into area. So this value here is 43.2. Same thing M2 also 43.4. So now it's a total force. How much need here is total weight of the liquid. So 9.89 into the volume of the displacement. So this value. So here just you have this value volume of the plate here this. So again how much 25.43. So this value 40 total weight how much 40 minutes subtract this much. This is here after just additionally you are getting here this. So 40.53 plus how much load is 80.4 plus initially that is 14.57. So total force also calculated this the 0.97. So this is vertical type rate. Horizontally vertically totally will be different here. Okay. Thank you.